Hi boys and girls, this is lecture 1.4 in Unit 1. The topic of this lecture, quadratic functions. Before we begin our discussion, however, notice the helpful calculator symbol has been removed. Whether this makes you happy or sad, the fact remains that for the assignment associated with this lecture, there are portions where you will be able to use a calculator and other portions where you will not be able to use a calculator. You may wonder why there's such a big deal about when you are allowed to use a calculator and when you are not allowed to use a calculator. Remember that everything we do in this course is designed to prepare you for the AP exam. On over half of the AP exam, no calculator is allowed. Therefore, in this course, every unit exam has been constructed similarly. Portions where you are allowed to use a calculator and portions where you are not. Therefore, the instructions I give you on each assignment as to when to use your calculator and when not to use your calculator are to help you get prepared for the unit exam where you will be doing problems with no calculator. Therefore, I'm going to ask that you follow my specifications regarding calculator use in order to be best prepared for each unit exam. All right, let's talk about quadratic functions. A quadratic function is a function which can be written in the standard form y equals ax squared plus bx plus c. Of course, this differs from linear functions because remember, with linear functions, there was no exponent. With no exponent, you don't get any curvature in your graph. But once you start adding an exponent, 2, 3, 4, whatever, you will get more and more complex curves in your graph. The graph of this quadratic function is called a parabola. And the parent function for the family of all quadratic functions is f of x equals x squared, which I have graphed here. This is the graph of a parabola. Of course, both of these are graphs of parabolas, but this one is the parent function where the vertex is centered at 0, 0. The classic shape. This is one of my favorite graphs. This beautiful symmetry and lovely curvature. It's so appealing. Notice I have a table of values here so you can see how this curve has taken shape. You have negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. The lowest or highest point on a parabola is called the vertex, and for the parent function, the vertex is 0, 0. We also have another feature, the axis of symmetry, which I've drawn as this dotted line here. It divides the parabola into mirror images and passes through the vertex. The axis of symmetry for this particular function is x equals 0. Now I want you to notice that this is an equation of a line. I'm not just saying an x coordinate is 0. I'm saying x equals 0 is the equation of this vertical line. It will always match the x coordinate of the vertex since the vertical line goes through the vertex. Other features of the parabola are the x-intercepts. These are also called roots, zeros, or solutions. And after we're finished graphing the quadratic and get to solving them, we focus more on this aspect of the graph than anything else. Here are a few other characteristics of the graph of y equals ax squared plus bx plus c, a quadratic in standard form. The graph opens up if a is greater than 0 and opens down if a is less than 0. Therefore, if this leading coefficient is positive, it's going to open up. If it's negative, it's going to open down. The graph will be narrower than the graph of the parent function y equals x squared if the absolute value of a is greater than 1, and wider if the absolute value of a is less than 1. Therefore, if this number here is a 2, a 3, or a 4, something like that, it's going to be a narrower parabola, whereas if it's a 1/2 or a 1/3, it would be a wider parabola. The axis of symmetry is x equals negative b over 2a, and the vertex has x coordinate negative b over 2a. You need to memorize this because that's where we get the x coordinate of the vertex when the equation is in standard form. That will be important for graphing. And finally, the y-intercept is c. Whatever c is, the point 0, c will be on the parabola. That is the y-intercept. All right, let's try graphing a couple of quadratic functions. Notice the first one is given to us in standard form. So the first thing we're going to want to do is discover what the x-coordinate of the vertex is. The vertex is the centerpiece of the parabola. Therefore, we need it to be the centerpiece of our table of values. Since this is a, 2 is a, and negative 8 is b, our vertex is going to be negative 8 over 2 times 2. This is a positive 8 over 4, which means the x-coordinate of our vertex is 2. Now, as I said, centerpiece of the table, therefore put it in the center of the table. Now list a couple of integers on either side, 0, 1, 3, 4. Now let's find the y values by plugging in each x value. This is going to be 6. In fact, that functions as our y-intercept. We already knew that that was a point on the parabola. If we put 1 in, 2 minus 8, negative 6 plus 6 is 0. Putting in 2 gives us 8 minus 16, negative 8 plus 6 is negative 2. 3 squared times 2 is 18 minus 24, negative 6 plus 6 is 0. And then 4 squared, 16, 32 minus 32 plus 6, another 6. So 0, comma 6, 1, comma 0. Oops. Let's make that 1, comma 0, 2, comma negative 2, 3, comma 0, and 4, comma 6. Now I don't have a parabola tool, so I just have to freehand this. Hopefully it'll look something like the parabola. I definitely want to do it justice. And there you have it, boys and girls. Now notice it's narrower because the leading coefficient was a 2. It opens upward because it was a positive number as well. You would definitely want to label the axis of symmetry, draw a dotted line going through the vertex, label it with its equation, in this case x equals 2. Label the vertex as well, 2, negative 2, and label the solutions if you can find them. This would be a graph that you're doing manually without a calculator, so if the solutions are integers, you can name them. In this case, they are. Notice the 0 in the table as a y-coordinate gives you the clue that these are zeros. 3, comma 0, and of course 1, comma 0. And this is the type of thing you would be expected to do without a calculator. Now let's go to this second quadratic. Notice it's in a different form. This is called vertex form or parabola form. It's y equals a, x minus h, quantity squared plus k. And when it's in this form, hk is the vertex of the parabola. The x-coordinate will be the opposite sign of what you see. The y-coordinate will be the same sign. So this is negative 1, comma 4. But I want to draw your attention to the fact that this is simply a series of transformations that have taken place from the parent function y equals x squared. This is a horizontal shift, a vertical shift, and a reflection, a downward facing parabola. In your table, again, the centerpiece is the vertex, and then list 2 integers on either side so that you can find several other points for the parabola. Plugging them in one at a time, 1 plus 1, 2 squared, negative 4 plus 4, 0. 0 gives you 1 squared, negative 1 plus 4 is 3. Negative 2 plus 1 is negative 1 squared, positive 1, but then negative, plus 4 is 3 again. Negative 3 plus 1, negative 2 squared, positive 4, but then negative again, plus 4 gives you 0. So we have 1, comma 0, 0, comma 3, negative 1, comma 4, negative 2, comma 3, and negative 3, comma 0. Connecting those dots gives you your classic downward shaping parabola. I feel badly that I'm not able to do a better job freehand graphing this for you, but I'm sure on your paper you have lovely parabolas taking place. We want to label the axis of symmetry. In this case, it's going to be x equals negative 1. Also the solutions, if you can see them. In this case, we have negative 3, comma 0. And 1, comma 0, and of course, last but not least, the vertex. Again, these would be graphs that you would be expected to do without a calculator. Fun. Now let's discuss quadratic equations. Quadratic equations can be written in the form ax squared plus bx plus c equals 0. Notice the difference. Instead of equaling y, equaling 0. That makes it an equation. Now let's briefly, before we finish that definition, discuss what is the difference between a quadratic function and a quadratic equation. And I've shown both of them to you here. But theoretically, let's understand that while this was a y, then this function, of course, has several ordered pairs, which would make this a true statement. But once we have changed the y to a 0, now we're forcing the quadratic to tell us only the x coordinates, which would correspond to a y value of 0. Of course, those are the x-intercepts, or the solution. Therefore, solving a quadratic equation means to find the zeros, also known as roots, solutions, or x-intercepts of the function. There are several methods for solving quadratic equations. Graphing, notice in the last two graphs that we constructed, we were able to visually inspect the graph and see what the solutions were. Of course, that's not always the case, but sometimes that will work for you. However, factoring, completing the square, and quadratic formula are three algebraic methods we can use to solve a quadratic equation and get roots. This leads to another characteristic of quadratics. How many solutions should we expect to see for a quadratic equation? It turns out there could be one, two, or none. Now, in the past two graphs that we constructed, we had the situation where it crossed the x-axis 2 times, as in this example as well. When that happens, there are 2 x-intercepts, therefore 2 solutions. But sometimes a parabola will just touch down on the x-axis, only intersecting it 1 time. In that case, the vertex would be the only solution. And there are other parabolas that don't cross the x-axis at all, which would result in imaginary solutions. Let's practice solving some quadratic equations. Since we've already graphed a couple of quadratics and determined solutions there, we'll start with factoring. When you're solving quadratic equations, the two types of factoring that you'll primarily use are factoring a trinomial into 2 binomial factors, or taking out a greatest common factor. In letter A, we have that first example where this is going to factor into 2 binomial factors. Remember that you would look at the factors of the leading coefficient, the factors of the constant, and some combination in some order would be the correct binomial factors. I'm going to try 5x and 3x. And then since I'm trying to get a -2 in the middle, let me make this a 4 and a 2. 10 and 12 would give me 2, a -12, a +10. That's factored correctly. But since it's set equal to 0, now you need to make 2 little mini equations with each factor set equal to 0. That means one of our solutions is 4/5. Take the other factor, make a mini equation with it set equal to 0, and the second solution is -2/3. Now you can never get away from the fact that these are actual x-intercepts on the graph. So for this particular graph, if these are 1 and -1, it's crossing the x-axis in these two locations. Since it's an upward facing parabola, something like this. So it always has to be tied back to the graph of the parabola. For letter B, we'll be able to take out a GCF, which is 11, leaving x squared minus 4, which is difference of squares, which means we can factor further, x minus 2, x plus 2. Now that we have factored this quadratic completely, we can make little mini equations, but only with the factors that have variables in them. We don't need to worry about the 11. In fact, if you think of it this way, dividing both sides of the equation by 11, since the left side is 0, just results in 0 equaling only the remaining 2 factors. So that's why at this point, since 11 is a constant, you don't need to worry about it. Let's make the 2 little mini equations. X minus 2 equals 0 results in x equals 2 as one of our solutions. And x plus 2 equals 0 results in x equals -2 as the other. And again, these are the x-intercepts of this particular graph. Now let's go to completing the square. Completing the square, square referring to what? A perfect square trinomial. Turns out that a perfect square trinomial is a special trinomial that's formed when 2 of the exact same 2 binomial factors are FOIL together. This would be x squared plus 6x plus 9. And these are special trinomials with special properties, but the one that we're interested in is the fact that you can write this as x plus 3 quantities squared. Being able to do this would allow us to solve these equations. So these are not perfect square trinomials, but let's create one and complete the square, the perfect square trinomial. We'll keep the first 2 terms of the trinomial, and then move the third term, the constant, over to the other side since it isn't the constant we need to complete the perfect square trinomial. Notice that half of the coefficient of the x term squared is the constant. So let's create that scenario here. Half of negative 12 is negative 6, squared is 36. So if I add 36 to those two terms, definitely make sure you do it on both sides of the equation. I have created a perfect square trinomial. I have completed the square. I know this now factors into x minus 6, which can be written this way. The right side is 31, but this allows me to take the square root of both sides. The square root and the exponent cancel, leaving me x minus 6 is equal to plus or minus the square root of 31. And when I add that 6 over, I end up with my two solutions, 6 plus or minus the square root of 31. Strange, irrational solutions, yes, but if you graphed this parabola, you would see it crossing the x-axis in two places, and these two whack little decimals are the places where it is crossing. Now let's complete the square for letter D. It turns out that if the leading coefficient of the quadratic term is not a 1, we can't complete the square. So let's make that situation happen by dividing everything in this problem by 2. I get k squared plus 8k, and then I'm going to keep the constant that doesn't complete the square on the right side of the equation. Remember, half of the middle term, 4 squared, 16. That is the constant I need to complete the perfect square trinomial. Now that it's a perfect square trinomial, I can write it as k plus 4 quantities squared. The right side is 10. I can now take the square root of both sides, resulting in k plus 4 equals plus or minus 10. Don't forget the plus or minus. That's where the two solutions come from. And subtracting 4 from both sides gives me negative 4 plus or minus the square root of 10. Again, this is a parabola with two irrational solutions, strange decimals though they might be. Now, before we move on to the quadratic formula, let's take a moment to talk about simplifying radicals and imaginary numbers. Now that these radicals are cropping up, we need to know how to handle them. Here are parts of a radical. This is the radical expression. The number here is known as the index. If no number is there, the default index is 2, which is the square root. The number underneath the radical is called the radicand, and here is the radical symbol. A square root is simplified if the radicand has no perfect square factors other than 1, and if there's no radical in the denominator. And when we're dealing with quadratics, it is square roots that we'll be dealing with primarily. However, I gave this example as well because, of course, simplifying radicals doesn't only involve simplifying square roots. But let's look to see what we would need to do in the case of simplifying the square root of 54. Since the only numbers that will actually come out of a radical are perfect squares, like 1, 4, 9, 16, 25, etc., you would hope that your number is on that list. 54 is not a perfect square, but don't give up hope. We can divide it into a product of two parts, a part that is on the list and a leftover part. So we notice that 9 is a perfect square, and 9 times 6 is 54. So we divided it into a part that can be simplified by the radical. Square root of 9 is 3, and the leftover factor stays inside. So 3 square root of 6 is the simplified version of 54. Now, square root of 54. Now, if your index is not a 2, if it's a 3 or something larger, you're dealing with a different set of numbers. When the index is 3, we're dealing with perfect cubes. 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, etc. And the only thing that will come completely out of a cubed root radical is a perfect cube. Of course, 54 again is not on the list, but it can be divided into a number that is on the list and a leftover factor, the cubed root of 27 and the cubed root of 2. So the cubed root of 27 is 3, and the 2 is not going to come out of the radical, it's going to stay underneath. But I also have some variables under here. Notice that if my variable had an exponent of a multiple of 3, then those variables would be able to be simplified by the cubed root radical. Since x squared doesn't even have enough multiplicity to come out of the radical with the index of 3, these x squareds stay unsimplified. However, y to the 5th can be written as y cubed times y squared. Since I can take the cubed root of y cubed and get y to the 1 power, I'm able to bring one y on the outside, leaving two leftover y's on the inside. And what if the number under the radical is negative? This leads us to the set of imaginary numbers. The imaginary unit is the letter I, which is equal to the square root of -1. If the number under the radical is negative, first separate it into the imaginary part times the real part. And since the square root of -1 is I, this becomes I squared of 24. I often say when there's a negative under the radical, take the I out, which is basically removing the imaginary portion. Now we can break this down using regular methods. This breaks into 4 times 6, the square root of each. The I is just outside waiting, and when you take the square root of 2, square root of 4 and get 2, it comes out to join the I outside, and the factor 6 remains under the radical, and that is the simplified form of the square root of -24. This brings up the age-old feud between the imaginary and the irrational numbers. Unfortunately, there are far too many instances in history of smack talk between the two sets of numbers. The last method for solving quadratic equations that we're going to discuss is the quadratic formula. If your quadratic is in standard form, then the coefficients a and b and the constant c can be plugged into this formula to generate your solutions. You may have learned a song to help you memorize this formula, but in case you haven't, I'm going to teach you one right now. These are snaps. -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now, you may have thought a famous singer came in to sing that song to you, but it wasn't a famous singer, it was just your math teacher. But now you have a little melody to help you memorize the formula. Perhaps you'll make this your ringtone, or you'll put it on your iPod, or maybe just play it over and over and over again in this beautiful video. However, it is important to memorize this formula. Now that we have it memorized, let's go apply it to this example. A is equal to 4, B is equal to -8, and c is equal to 1. The formula says your solutions will be -b, which is -8, plus or minus, then b squared, so in this case -8 squared, minus 4 times a times c. And all of this will be over 2a. Now, when simplifying the quadratic formula, you're probably not going to have any trouble simplifying that section or this section. But underneath here, we're prone to make careless errors. Anytime you're squaring an answer, the number should be positive. But often you might see -8 squared and someone would write down -64 as your answer. That's a careless error, should not happen. Also, when you're multiplying these three numbers together, sometimes we're not sure if we're adding or subtracting. Well, here's a way to help you remember. There's always one negative in the formula. So if there's 1 or 3 negatives altogether, you'll be subtracting a number. But if there are 2 numbers that are negative, then you'll be adding. So hopefully those little tips will help you avoid careless errors when you're simplifying. So underneath the radical, a positive 64, and since there's only one negative, this will be minus 16 all over 8. Simplifying further, 8 plus or minus the square root of 48 over 8. This breaks down into 16 times 3, square root of 16, square root of 3. Simplifying further gives us 8 plus or minus 4, square root of 3 all over 8. And our final step in simplifying will be to reduce those three outside numbers. 2 plus or minus the square root of 3 over 2 is your solutions. Now, if you actually made the decimal 2 plus the square root of 3 over 2 and the other one 2 minus the square root of 3 over 2, you would find that this is indeed where this parabola crosses the x-axis. And now for our last example. First of all, notice it's not in standard form. We've got to move that 5 over first. The right side must be equal to 0 before we get started. Now, that means A is -1, B is 4, and C is -5. The formula says that we will take -4 plus or minus the square root of 4 squared minus 4 times a times c, never make that radical sign long enough, over 2 times negative 1. Let's go ahead and continue simplifying and make sure we avoid careless errors. Negative 4 plus or minus, underneath the radical, we're going to have 4 squared, which is 16. And since there are 3 negative signs, this will be minus 20 over 2 times a negative 1. And simplifying further, negative 4 plus or minus the square root of negative 4 over negative 2. Now we want to recognize that this is an imaginary solution, but go ahead and take the I out of the radical. So this will be negative 4 plus or minus I square root of 4 over negative 2. And then when we simplify the square root of 4, we end up with plus or minus 2i over negative 2. Now let's divide negative 2 into both of those terms for a final simplified answer, and we'll have 2 plus or minus I as our two imaginary solutions. Now this graph, downward facing, because the leading coefficient is negative, doesn't cross the x-axis at all, so something like that. Imaginary solutions. That's the end of today's lecture, boys and girls, but let's end with this final thought. Parabolas describe the path of projectiles, perhaps bouncing balls, as you see here, lighted up so colorfully, perhaps porpoises leaping in the ocean, or extreme motorcycle stunt motion, or even water, as water droplets are projectiles as well. You can see the parabolic shape, and this squirrel is about to actually drink a parabola. How cool is that? Other things you might see, angry birds. That's right, boys and girls. That is also parabolic motion as well. So as you're walking around in the world in these next few days or months or years of your life, take note of the parabolas that are all around you and watch out for the angry birds. God bless you, boys and girls.